Welcome. In this video, we are going to explore the best practices for C++ development. We will focus on coding standards and practices to write modern, efficient, and maintainable C++ code. Get ready to dive into the world of modern C++ development. Why should we even bother with best practices? For developers, following these guidelines reduces the cognitive load when reading code, which makes it easier to understand and work with. It also makes code easier to maintain and extend over time. Best practices help prevent common bugs and vulnerabilities that can compromise the security and stability of the application. They also improve collaboration in team environments, making it easier for developers to work together. And they facilitate knowledge transfer between team members, ensuring that everyone is on the same page. For projects, following best practices enhances code quality and reliability, which leads to more robust and dependable software. It also reduces technical debt over time, which saves time and money in the long run. Best practices improve performance and resource usage, making the application faster and more efficient. They also simplify debugging and troubleshooting, making it easier to identify and fix problems. And finally, they enable faster onboarding of new developers, allowing them to quickly become productive members of the team. One of the fundamental aspects of writing clean and maintainable code is following clear and consistent naming conventions. Let's take a look at some examples. Consider the code on the left, where variables are named a, x1, s, and f. These names are not descriptive and do not convey the purpose of the variables. Similarly, the function name proc is vague and does not indicate what the function does. In contrast, the code on the right uses descriptive names such as user count, initial position, username, and is active. These names clearly indicate the purpose of each variable. The function process user data also has a clear and descriptive name. By using clear and consistent naming conventions, the code becomes easier to understand and maintain. Memory management is a crucial aspect of C++ programming, and using smart pointers is a best practice to avoid memory leaks and other memory-related issues. On the left, you can see an example of manual memory management where a resource is allocated using the new keyword and later deallocated using the delete keyword. However, if an exception occurs between the new and delete calls, the memory will not be deallocated, resulting in a memory leak. On the right, we have the improved version using smart pointers. We create a unique pointer to manage the resource. When the unique pointer goes out of scope, the memory is automatically freed, even if an exception occurs. This eliminates the need for manual memory management and prevents memory leaks. Resource acquisition as initialization, or RAII, is a fundamental concept in C++ for managing resources such as files, sockets, and memory. Let's compare the traditional approach to the RAII approach. On the left, we have an example of manual resource management using the fopen and fclose functions to open and close a file. However, if an exception occurs after the fopen call but before the fclose call, the file will not be closed, resulting in a resource leak. On the right, we have the improved version using RAII. We create an input file stream object to manage the file resource. When the input file stream object goes out of scope, the file is automatically closed, even if an exception occurs. This ensures that the file is always closed properly and prevents resource leaks. Modern C++ offers several features that can make your code cleaner, more efficient, and easier to read. One of these features is auto for-type inference. On the left, we can see verbose iterator declarations. Declaring iterators explicitly can be cumbersome, especially when dealing with complex types. Also, repeating type declarations can make the code harder to read and maintain. On the right, we can see the improved version using auto. Using auto allows the compiler to automatically deduce the type of the variable, making the code more concise and readable. Even better, using range-based for loops. In this example, the code iterates over the numbers vector using a range-based for loop, which is even cleaner and more readable than using iterators. This modern C++ feature enhances code clarity and reduces redundancy. Effective error handling is essential for writing robust and reliable C++ code. In this section, we will explore the best practices for handling errors using exceptions. In the code on the left, the openFile function returns an integer error code to indicate success or failure. The calling function must then check the return code and propagate it up the call stack. This approach can lead to verbose and error-prone code. Now let's look at the right side. In this case, the openFile function throws an exception if it fails to open the file. The calling function can then catch the exception and handle the error appropriately. This approach is cleaner and more concise than using error codes. Designing functions with appropriate parameter passing techniques is crucial for writing efficient and maintainable C++ code. Let's take a look at some best practices for parameter passing. The code on the left shows two examples of inefficient parameter passing. In the first example, the process data function takes a vector of integers by value, which means that a copy of the vector is created when the function is called. This can be inefficient for large objects. In the second example, the print data function takes a pointer to a vector of integers, which allows the function to modify the original data. However, this is not always desirable. On the right, in the process data function, a reference is used to pass the vector of integers, which avoids the unnecessary copy. In the print data example, the vector of integers is passed by constant reference, which ensures that the function cannot modify the original data. Const correctness is a fundamental principle in C++ that involves using the const keyword to indicate when a value or object should not be modified. Let's compare the code with and without const. The code on the left shows an example of a function that calculates the average of a vector of integers. However, the function does not use the const keyword to indicate that the vector should not be modified. This can be misleading to the caller of the function. On the right, the function uses the const keyword to indicate that the vector should not be modified. This clearly communicates to the caller of the function that the vector will not be changed. Okay, let's recap the key areas we've covered in C++ best practices. For code quality, use clear naming conventions for readability. Follow RAII principles for resource management. Apply const correctness consistently. Write self-documenting code with meaningful names. For memory safety, prefer smart pointers over raw pointers. Use containers instead of manual arrays. Avoid manual memory management. Leverage move semantics for efficiency. For modern C++ features, use auto for type inference. Adopt range-based for loops. Leverage lambdas for cleaner code. Utilize structured bindings where appropriate. For error handling, use exceptions for error conditions. Consider std optional for nullable returns. Implement proper cleanup in all code paths. Provide meaningful error messages. Consistent application of these practices leads to more maintainable, efficient, and robust C++ code. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.